Well, good morning. Welcome back. Let's get started. Hope your rest was well. Who just joined today? Raise your hands. Oh, we have a sizable group. And also from today, we have live streaming. So we have cyber participants in the conference. I think it's a good idea for me to do a short recap for what happened yesterday. I thought we had a quite exciting and a dynamic day. We started the morning session, which was focused on technical insights, and the afternoon session facilitated by Tim Nargis from University of Washington, working on community building. A few highlights. From the morning, we had the gateway hands-on. We got all the group of people in the room pushing through over 50 analytical tasks on the gateway simultaneously within about 5 to 8 minutes period, without any technical training prior to that experience. There's only one task failed. Let's give our technical crew in the CyberGIS project team applause. So that was hard work for the technical crew in the CyberGIS project for the last 2 quarters to ready the infrastructure, to do the plumbing, and to make cyber infrastructure disappear, as Mark Gahigan yesterday mentioned, as our grand field campaign, if you will. And then we followed with introduction to fundamental middleware components, GISolve, we're researching, developing in the project, and we introduced the Open Services API, which as a layer of abstraction to simplify access to cyber infrastructure and CyberGIS, particularly from application development point of view. So if you are application developers or if you're scientists are familiar with the scripting, familiar with some client programming, those kinds of interfaces are custom to your needs. And we have a social scientist, external collaborator, Kalev Litarju, brought together a very interesting social media analytics example use case driving the development and research for the Open Services API. You saw very interesting results presented, pushing data through the Open Services API, getting the analytical results back. That was quite remarkable, I thought. And you will hear more details about that use case tomorrow, the main day of the conference. That was a highlight of the project experiences, and you will get more details into that example. And then we went on to the CyberGIS toolkit, which is the plumbing deeper into the cyber infrastructure tier of knowledge. And we introduced a number of cases, primarily focusing on parallel I/O, because we recognized the scalability of getting data across different resources in the cyber infrastructure. And we talk about PyCell as an open source model, working on a car-plate map optimization case study. So with that, we will transition to the afternoon session. That was a community building process. We had 3 self-organizing groups emerged, thanks to Tim Niger's structured participation, idea and process, the big data group, the sustainability information science group, and the other groups, the use case and killer apps. I thought all 3 groups had a very dynamic interactions and discussions, and thanks to Mark Gahigan, Mark's over there, and Nancy Wixdeer and Bill Apley and Steve Prager for running the groups, facilitating the discussions, and already received some of your notes you took yesterday. That was really appreciated. So with all that, we're moving to the second day, which is squarely focused on research advances, fundamentals, in the synergistic context of CyberGIS and the spatial temporal synthesis research. Any questions from the audience so far? about the conference and about what happened and about any ideas you might have would make our experiences more fun and interesting? 1, 2, 3. No. Logistics today, because we have live streaming, if you have any questions, either you would get a Mac, microphone, passed to you, or whoever speaks is gonna repeat that questions on the podium. So that's gonna make the interactions available to the live stream. All right, so it's my great pleasure to start the next session, which is our keynote session. We have 2 keynote speakers. The first keynote speaker is Dr. Mike Goodchild. I've learned over the years there's a simple script of introducing Mike, is that Mike does not need introduction or it's too complicated to introduce him. And then we pass on. I just want to add a few personal notes from particularly my personal experiences. I already applied that script, so that part is done. Mike, as lots of us have known, recently retired. He is Professor Emeritus at University of California, Santa Barbara, currently, and obviously he's still very active, helping so many things, it's too many to count. He has just collected so many accolades over his long, distinguished career. Again, too many to count. Just to name a few, member of the National Academy of Sciences, he's won a Nobel Prize in geography. So just too many things, very hard to mention. Back to my personal notes, when Mike was leading the NCGIA initiative, I was in my graduate school at Peking University. I think that initiative had a lot to do with my major switch from computer engineering to GIScience. And even from then, I was watching what Mike was doing. And up to recently, we started this NSF CyberGIS project. A major reason why we are here. Mike serves as the chair of the Science Advisory Committee. I was just so privileged to learn so much from Mike in the past 2 years also. And I got the impression he's just so approachable. I never heard of anything say, oh, really? It's always sure, yes. Give an example of this, very related to this conference is, I was asking Mike only less than 2 weeks ago. I said, oh, in our schedule, we have a little bit of gap. Would you be okay to deliver a keynote? Within an hour, the return email says, sure, that's fine. Without further ado, Mike.
Thank you, Xiaowen, and thank you for that introduction, and thank you for the invitation to do this. I have 2 apologies to start. First, some of these slides will be familiar to the few of you who are at the AAG CyberGIS and Health workshop in San Diego 10 days ago, so I apologize for that. Secondly, I don't have much eye candy. A lot of these are text, and again, I hope nevertheless I can keep your attention. I want to talk first about the vision of cyber infrastructure, and then ask what that has to do with GIScience. So let's first try to clarify what we mean by cyber infrastructure, or specifically cyber infrastructure supported science. And there are a number of elements to this, and I think all of them are relevant in one way or another here. The first is that science in the future, supported by cyber infrastructure, will be done by teams studying complex questions. And the subtext there is that we have run out of simple questions, and we are left with phenomena that are fundamentally complex and will need to be studied. These teams will be distributed across disciplines. Those disciplines have disparate practices, they use different languages when they talk, and so there are major problems of interoperability and building community across disciplines. These teams will be distributed geographically, and so powerful communication links will be needed. We won't always have the opportunity to bring everybody together into one room. And they may be distributed temporarily as well, so much of the communication will need to be asynchronous. And that's something that, of course, we're very used to in this field. This second element would be that cyber infrastructure promises access to vast repositories of data, possibly close to real time. Using powerful search tools, there will be comprehensive documentation which will deal with issues like metadata and provenance so that data can be shared across widely disparate communities who don't necessarily share understanding of lineage and so on. Third, there will be access to powerful software tools, and of course that was a major aspect of yesterday's discussion. The tools will allow for manipulation, analysis, modeling. The tools will be interoperable, and it will be easy to match them to data. Right? All of these are part of the vision, right? And we're not talking about the degree to which they're currently true. Number 4, there will be powerful computation, and on the network there will be supercomputers, and so the kinds of technology we saw yesterday will be part of the vision of cyber infrastructure. The communities will be well connected, and members of the communities will be skilled in the use of cyber infrastructure and the use of these tools. Recruitment will be easy, so putting together a team to study a complex problem, the formation of the team will be straightforward because it will be easy to find the necessary people. Right? Specializations will be well defined, and so it will be easy to find, for example, a GI scientist when one needs one. And then finally, there will be efficient methods of knowledge sharing, because the knowledge that will be accumulated through the use of cyber infrastructure, the scientific knowledge, will be easily shareable across widely distributed communities. Right? So those 6 elements, I think, really define the vision of cyber infrastructure. Right? So what's special about spatial? Right? Because that vision is purely generic. So we have to ask, in this context, is there a specifically spatial perspective? Is there a specific case for CyberGIS, where G stands for geographic, as distinct from, let's say, a case for cyber geriatric information systems or cyber Gulf information systems, right? There has to be some specific case for geographic information systems. And that, I think, is a major question for us. And let's recognize that before we even begin that discussion, in some ways, GIS is already ahead of the field. Right? The state of infrastructure, when it comes to the geospatial world, is already very rich. Right? National Spatial Data Infrastructure concept was published in 1993. The metadata standard in this field dates from 1992. There are many domains out there that don't yet have a metadata standard. Geolibraries have existed since 1993, geoportals, the OGC standards are very rich and have evolved dramatically over the past couple of decades. And there is in this field a tradition of data sharing, which goes well beyond the tradition of data sharing in many disciplines. Part of that is due to the fact that much of the data in our domain is already in the public domain. Cases like the Feist decision, which was the decision that it was impossible to copyright geographic data because geographic data consisted of facts. That decision has led to, I think, a tradition of widespread sharing of information in this domain. So all of this is already in place. And so, in many ways, CyberGIS is not a qualitatively different thing. It's a consistent continuation of movement in the same direction. It's a continuation of the momentum which has existed in this domain, I think, for a long time. Another thing that's true of this domain and not others is community engagement, because GIS functions, some GIS functions, are essentially available to all these days. People love maps. Volunteer geographic information has been a phenomenon of the past few years. But, and this I think is a major but, in the scientific community, the engagement is not as uniform. Much of science is essentially about generalizing away from space and time. So a discipline that is concerned with space is not necessarily part of the basic scientific enterprise. Physics is about finding things that are always true, irrespective of space and time. It's about taking phenomena embedded in space and time and abstracting away from space and time. So for that reason, I think we would say that there's been a very variable take-up of GIS in the scientific community. It's been very strong in some disciplines, but not in others. Perhaps also there's a belief that what we deal with is intuitively obvious. There are no widely recognized theories or principles in our field. There's a reluctance perhaps to see GIS as comparable in intellectual depth to other aspects of infrastructure such as statistics. Right? So I think there's a sharp contrast here between the citizen and community engagement and the scientific community and engagement. Right? So what are the elements then of a geospatial cyber infrastructure? And I think we need to explore this question and to be clear in our own minds about what the answer might be. Right? So number one, base mapping. We need easy-to-use mapping tools, and we've made enormous progress in that direction, represented, for example, by the Google Maps API, by ArcGIS Online, by the widespread availability of boundary files, which make it very easy for people to make maps. Right? We have extensive gazetteers and point of interest databases. So in sources like geonames.org or the Google Maps API, we have enormously rich databases of points of interest on the Earth's surface. We've also achieved, I would argue, almost perfect interoperability of georeferencing styles. The weakness perhaps is in the parsing of text, but in other areas like conversion between street address and latitude-longitude, between UTM and latitude-longitude, we have almost perfect interoperability at this point. We have geocoding services, which are very successful. And we have powerful analysis packages such as the Geoda, Arizona State's Geoda, ArcGIS, R, MATLAB, etc. So there's an enormous richness here in what we already have in the way of cyber infrastructure in this domain. So go to the Google Maps API and you find enormously rich and dense points of interest and information about those points of interest. Very easy these days to make a map using counties. Imagine how long that would have taken 4 decades ago to make a simple map like that. It would have taken weeks. But here, this is an interesting map. This is the percent uninsured by county in 2006. And notice the upper Midwest, which is almost completely insured. Notice Massachusetts, which is almost completely insured. Thank you, Mitt Romney. And notice Santa Barbara County, which has a surprisingly high rate of uninsured, which I was rather surprised at. And Geoda, this is unfortunately a rather early version of Geoda, but demonstrating the power that Geoda now has in analyzing geospatial data. Right? So what are the other elements then of geospatial cyber infrastructure? We have extensive data in the area of geodemographics. Census data is widely available for mapping. We have access, for example, any NIH PI has access to the geodemographics data in PRISM, Esri's Tapestry, etc. And the National Spatial Data Infrastructure, which I said has existed already for 20 years, its 7 base layers are widely available in the public domain. Okay. So why the interest in CyberGIS? What's missing? Because we already have a lot. Well, first, speed up. One of the arguments made for CyberGIS will be speed up. That case, though, seems to me always somewhat difficult to make. Clearly, there's a cost associated with speed up, with transitioning to the kinds of architectures which give high rates of speed up. What is that cost worth? What is the effort worth? And I've sat, for example, through presentations which have argued for new architectures and have demonstrated a factor of 3 speed up. And I wonder to what extent my 20 minutes listening to the presentation was worth times 3 speed up. I wonder if I couldn't just have had another cup of coffee and used conventional architectures. So it always seems to me the speed up case is not that clear. It clearly is a viable case in some areas, but probably not in others. So perhaps we need to explore other arguments. And I want to present a number of other arguments. Right? So number 2 is scale. CyberGIS, the kinds of architectures in CyberGIS allow us to scale up our analyses and our modeling. Right? So it allows us to perform simulations and develop models on larger numbers of elements. And I always remember Dave Maidment some years ago arguing that essentially there was a ceiling of 10 to the 6th in his modeling and simulation in hydrology. It didn't matter whether you partitioned the 10 to the 6th, how you partitioned it between space and time, whether you had 10 time intervals and 10 to the 5th spatial elements or whatever, any combination. That was essentially a threshold. Right? CyberGIS clearly allows us to go way above any such threshold. It also allows us, and I think this is perhaps more important, to make scale explicit. So to address problems such as the MAUP and the ecological fallacy, which essentially are a legacy of limited capacity in our computing systems. Right? Go to CyberGIS and you have the ability to have much finer spatial detail, much larger volumes of data. So the scale argument, I think, is a very viable argument. Because we can avoid shortcuts, and this perhaps is one of the more subtle points, but may in the long run be one of the most important. What is very difficult to realize is the extent to which our practices in computing have been in the past subject to shortcuts because our computing capacity was so limited. We did things only because we couldn't compute larger volumes of data. So what were those things? Here's 3 examples. We've used Pythagorean distance instead of geodesic distance because geodesic distance involves using trigonometric functions and they're slow. In a world of CyberGIS, that never needs to happen. All of our analysis can be done on a curved Earth. It's simply a legacy of the past of limited computing that we've done so much on a projected Earth. Right? That said, we don't have a complete set of analytic methods on the curved surface of the Earth. Many of our methods are strictly Pythagorean. So we need new methods. The late Rob Raskin did a very nice survey back in the 90s of the state of available methods for analysis on the sphere. It was quite a short list, and I don't think it's got much longer since. My proposition is simply, we never in the future will need to use Pythagorean distance with all the distortions that involves. And one can make the same statement about measurements of area or any other measurement that we use in GIS analysis. In a world of abundant computing, there is no need to divide and conquer. There's no need to artificially limit the size of study areas in order to produce something that's feasible for computation. With all that means in terms of the difficulty of generalization. Right? Do a study of a small area and you inevitably have a generalization problem, generalizing away from a small area. In the world of CyberGIS, we can analyze much larger areas. We can do, as we saw yesterday, view sheds on massive amounts of data, much larger areas than we could in the past. No need to restrict to least squares. The reason for least squares and many of the decisions that were made in the early days of statistics was mathematical tractability and therefore computability. We can go to a world of nonlinear optimization. We don't need least squares because the advantage of least squares was only that it produced easy mathematics. No need for parametric and inferential statistics. We can do everything using simulation and randomization tests. Many of these restrictions, I'm arguing, are a legacy of an era when computing power was very limited. And this is a very short list of what is actually a very long list of arguments that one can make along these lines. More reasons for interest in CyberGIS. Because the Earth's systems really are parallel. Humans and communities are semi-independent agents making simultaneous decisions. Forcing that into a serial world of computing was always artificial and was always distorting. In a world of parallel computation, we can make models of the world which are much closer to real-world processes. An argument that Mike Batty made, I think, about a decade ago. And because today's science problems really are more complex. They really do require multidisciplinary distributed teams. They really do require the kinds of cyber infrastructure that we're talking about developing. Yeah? So there's a few reasons, I think, beyond the speed-up argument. Some of them, I would argue, more powerful than the speed-up argument that support a move to CyberGIS. We heard quite a bit yesterday about new kinds of data, and there was much discussion late in the day about big data. And I think it's important to recognize, again, what some of the characteristics of big data are and why they require this kind of novel approach. Big data will be closer to real time. It will be a vastly increased volume. It will have poor and diminishing quality control. It will come from disparate sources. There will be no opportunity for lengthy synthesis by experts. That's something that's always happened in the geospatial world. The raw observations have always been synthesized by experts to create clean, well-documented products. That's not possible in the world of big data. There will be generally no metadata, no provenance where this stuff came from. And so there will be a very major need to automate quality control, to automate the production of metadata, automate provenance production. What are the characteristics of big data? And one often hears a three-way, the 3V discussion of big data. The first V is volume, right? We're talking about petascale, exabyte scale of big data. It's interesting to speculate on when we'll need to go to the next one, which is 10 to the 21st, which is already officially recognized as the zetta scale, and 10 to the 24th, which is the yotta scale. And I discovered yesterday, I was very intrigued by this, that the mass of the Earth is about 5,900 yottagrams. Which I think it's going to be interesting when we start talking about yotta scale, which is 10 to the 24th. Yotta, yeah. The second V is velocity, because the world of big data is a world of rapid change and necessarily rapid speed of analysis. Right? The second V. And the third V is variety, because the world of big data is a world of many sources of varied quality. Right? So that 3V discussion is something one often hears, but I think it really misses the true potential of big data. And for that, I think we need to think about new kinds of analysis and new kinds of knowledge creation in a world of big data. Right? Because in the world of big data, we will need new kinds of analysis. We will need analytic tools which work with data of unknown or variable quality. And think how often you, in analyzing data, have ever had to deal with the possibility that individual elements of data have varying quality. That's a different world from the world we've been used to. This is data which is much more suited to hypothesis generation than a hypothesis testing. It's more suited to the softer end of science rather than the harder confirmatory end of science. It's more about exploration. It's more about designing samples. It's more about induction. There's a temptation to think that this is a less important end of science. I would argue quite the opposite. I think this is a very important end of science. It's the end that will be supported by big data. It doesn't require the kind of rigorous sampling that the confirmatory end of science requires. There's clearly an increased role for machine learning in this world. But I think more fundamentally, all of this challenges the norms of science. And there was some discussion of this already yesterday afternoon, some aspects of this. And here are some of the ways in which I think it does that. In science conducted by teams, there has to be a collective responsibility. Every member of the team has to be responsible for the fact that the team's project follows the norm of science. How do you deal with plagiarism in a team? Does it mean that every member of the team has to check that everybody's output doesn't involve plagiarism? How is collective responsibility to be dealt with? We've grown up in a world in which science was an individual responsibility and plagiarism was individual. This is a very different world, a world of teams. We talked yesterday briefly about the black box, because in the world of big data, it's impossible for every member of a team to know all details of a project. It's impossible, therefore, to meet the standard of replicability. It's no longer going to be possible to report every scientific result in sufficient detail to support replication. And yet that's a standard we've always demanded of our science. So there's a need here to rewrite the methodology of science. It's a very fundamental set of issues that this raises. Experimental design is another problem, and poor data. Science doesn't teach us how to make discoveries using poor data. It always assumes that the data available to science is as good as it can possibly be. And in this new world, that won't be true. And that raises some very interesting questions. But I think perhaps the most fundamental set of questions have to do with new concepts of knowledge, because in this new world, knowledge will not be produced in the same kind of way. And in talking about this, I'm following a little bit David Weinberger, who's a research professor at Harvard. One of his books is entitled Too Big to Know. It came out fairly recently. And here are some of the points he makes that I think are most relevant to this discussion. He argues that the concept of knowledge creation has a very strong legacy. We have fixed practices which we've grown up with. And yet in a world that's rapidly changing, those fixed practices need to be questioned. One of those fixed practices, of course, is academic advancement. We have a very rigid system of academic advancement that counts papers published in the refereed literature, counts citations. Right? To what extent is that going to be possible in this new world? And Weinberger has a lot to say about that. One of the things he talks about is what he calls stop events. In traditional knowledge creation, there are events which stop the creation of knowledge. One of them is the publication in a learned journal, or the publication of a book. Once the knowledge has been accumulated and appeared on the shelves of a library, it stops, it's frozen. Right? His argument is that in this new world, there will be no stop events. Knowledge creation will be continuous. He also argues that all knowledge will be contested. In the world of big data, where nothing is certain, so all knowledge will be uncertain, in that world, there will be no stop events. Knowledge will never freeze. We're not talking about discovering things of the rigor of Newton's laws of motion. We're talking about making discoveries which will always be contested and uncertain. And that creates a very different perspective, I think, on knowledge creation. Okay. So let me shift gears a little bit and talk about this project. And if you agree with me that there's a very clear vision here, then how do we propagate that vision? First, we have to know why CyberGIS is important. And I'm going to argue that CyberGIS is important because it enables new applications, it enables new discoveries, it creates possibilities that were not realized before. So against that, we have to ask the question, has the case been made, or is this merely a matter of faith at this point? Do we, as a matter of faith, believe that CyberGIS will lead to new discoveries, or has that case been made? And this is very reminiscent of a period we went through in GIS in the early 1990s, when people were wont to ask questions like, can you point to an application of GIS which has led to a new discovery that could not have been discovered in any other way? We need a set of compelling examples of what could not be done without CyberGIS. And that's a very, very difficult criterion to meet. It's a very difficult hurdle to get over. For years, I used to quote some work in archaeology, which explained the distribution of burial mounds of the Iron Age in Britain based on viewshed, something that could not be done without GIS. And today, I would probably quote the work of Ann Knowles, and particularly her work on the Battle of Gettysburg. I don't know if you're familiar with this. It's in one of the books on GIS applications in history. When she announced that she was going to use GIS to study Gettysburg, everybody said, what on earth could you discover that's new about Gettysburg? It's been written about so often. You know, what she did was take the headquarters of both sides and the viewshed from those headquarters and show very convincingly that the North had a much better command of the battlefield because of the viewshed from its headquarters than the South did. The North was able to have a comprehensive view of the battle that the South was not able to do. A very compelling case, something that you could not have done without GIS. Of course, we could build a physical model, but we wouldn't do that. GIS makes it much easier to do that. Right? So what we will have to do, I think, is to come up with similar examples, compelling examples, of what you can do with CyberGIS that you could not do in any other way. Right? But I think we can go further in asking what it will take to propagate CyberGIS. And let me make a couple of points here. One is, I think CyberGIS must be more accessible than GIS, because it will be necessarily something people have to learn about. And in order to justify learning about it, you have to see a benefit. And that benefit has to be that it's more accessible. Right? What do we mean by more accessible? More accessible to a larger user community. In this world of CI teams, that means people in different disciplines. And unfortunately, and this is, I think, a general principle, advanced technology tends to move initially in the opposite direction. Initially, advanced technology becomes less accessible than the technology it tries to replace. And I think the evidence would be fairly clear at this stage in the development of CyberGIS. But only if we can make it more accessible will others be motivated to adopt it. That means then that the learning curve must be shorter. The user interfaces must be more intuitive. The technology must be interoperable across more knowledge communities. And against that, ask yourself, how accessible is GIS against those standards? And I think all of us would agree that GIS still is not as accessible as we would like it to be, certainly in its professional versions. So this is, I think, a major challenge. We have to make this new technology more accessible than the technology it replaces. And much of that, I think, comes down to the user interface. To support CyberGIS, service-oriented architectures, discovery of services, interdisciplinary research, we must somehow formalize functionality to a common language which is used to describe operations and which is interoperable across different platforms. And that's something we, I would argue, have not achieved in 40 years of GIS development. Let me just take one example, which is ArcGIS version 10. Here's the toolbox pulled down in ArcGIS version 10. And you probably haven't counted them, but there are 610 functions in the toolbox of ArcGIS version 10. And in 10.1, there's more than 800. And those are organized in a hierarchical fashion. It's a major challenge to navigate the hierarchy, and as a result, almost everybody searches. They do a keyword search for a tool if they're looking for one. They don't rely on the naming of the tools. If you look at how they're distributed across various categories, this in itself suggests the need for some work because, 615. Out of the 615, 178 are under one heading of data management tools, and only 2 are under the heading of data interoperability tools. That kind of non-uniform slicing of the pie suggests that there needs to be some more work on this. So what I'm going to suggest is that if one thought seriously about the user interface, what one would have is a focus on the questions users want to ask. So, for example, one of the things we have to teach in any GIS course is something like this. The idea that in order to answer question A, you need to use function B. That translation ought to be handled by the user interface. We ought to be able to specify the question rather than rely on the knowledge of the user to convert the question into the function. And of course, in reality, it's not just function B, it's function B1 followed by function B2 followed by function B3. And that, to my mind, as a GIS educator, is one of the most difficult things to get it over to a class. How do you translate a question into a set of procedures in this world? Now, here's just one example of Model Builder, and I just show it to illustrate the complexity that one has to go through in order to answer a question using the current user interface. One of the things that's intrigued me in this connection over the years is the series of books that Andy Mitchell has written on GIS analysis. They're a very successful, I think, set of books because they focus on the questions. There are now 3 of them. The 3rd one just came out this year. They cover much of spatial analysis, but they do it in a very intuitive way, which starts with the questions. What he doesn't do is convert the question into the GIS function. It leaves that to the reader. So that link is still not made. But it does intrigue me that they begin with questions. So here are the titles, for example, of the chapters of Volume 1. All of these, in effect, are questions about geographic information. So let me pose the question this way. If you had an infinite supply of computing power, which I believe we have or are about to have in the world of CyberGIS, how would you deploy it? And this is not to say that it's not a zero-sum game, because the amount of power is infinite, but every deployment requires resources, and that is a zero-sum game. How do you spend the resources of this CyberGIS project in order to address these issues? How do you deploy across the various options? On the assumption that you have an infinite supply of power. Right? Would you deploy on bigger simulation models? Right? Or would you deploy on synthesizing and analyzing larger quantities of data? Or would you deploy on tools that allow researchers to collaborate better? Or on making the user interface more accessible? And if you were to look at this from the perspective of the downstream deployment of CyberGIS, I would suggest that the last of those may be the most important. Right? And again, it will require resources, because the user interface has to be seriously rethought, redesigned, and that requires the deployment of resources. Right? I suspect that the temptation is to choose from higher up on the list. But I want to make the point that I think the last on the list is arguably as important as the others. So here's my dream of the CyberGIS interface of the future. It's personified Dr. Geo Analytics, and it allows you to ask Geo. Right? And you ask Geo, where are the counties with the highest percent uninsured? I know how to do that. I showed you the map that would allow you to do that. I know how to go through the steps of using a GIS to do that. That's the translation I'm looking for. Do these counties tend to be rural counties? Or, more generally, how is X related to Y when X and Y are spatial variables? Because you know and I know that the answer to that question depends enormously on whether X and Y are both columns in the same attribute table, or whether they have different spatial support. Because if they have different spatial support, a whole sequence of operations needs to occur before you can answer the question. So here's the focus that I'm trying to sketch out. And here's this is a ripoff on United Airlines. United Airlines has one of these expert interfaces. You can ask Alex questions. I want to ask Alex, what do they mean by momentarily when you're sitting in an airplane? It's the question I would most like to have an answer to. But I'm suggesting at the bottom there that we could ask Alex or ask Dr. Geo Analytics, do rural counties tend to have more uninsured than urban counties? So this is, I think, where we need to be investing some resources if we want to redesign a user interface to the point where CyberGIS goes away in the terms we've been discussing, or is at least as easy to use as GIS. So here, just to summarize, is an attempt at a prescription for a successful CyberGIS project. Number one, people engaged in the project need to think both as technically expert GI scientists and also as users. And that duality is extraordinarily difficult to achieve, of course, but we need to be thinking in both directions. This option came up yesterday, and the suggestion was you had to choose one or the other. My answer is there's no option but to choose both. We need to understand why CyberGIS is important and how to argue that, let's say to an anthropologist or an ecologist, and let's say in 30 seconds. All of us need to have that kind of resource. Above all, we need to simplify. Everything must be thought about in the context of simplicity. The product must be easy to learn and use, as well as being powerful and scientifically rigorous. Again, something that's extraordinarily difficult to achieve. And we must think ahead, because today's technologies will continue to evolve. Building CyberGIS on a foundation of today's technologies runs the risk that those technologies will go away in a fairly short period of time. So this must be constantly forward-looking. I think that CyberGIS is much more than a simple continuation of a move in a single direction. I think it really is a game changer. And I think I've made some of the arguments for that. Number one is that it really, if we do it well, will have us rethink many aspects of GIS, especially the user interface. It will change traditional practices. If we can recognize traditional practices for what they are, the legacy of the past, the legacy of earlier technologies, and rethink them. It will allow us to ask new questions that move well beyond the old questions. So the issue here is not the extent to which CyberGIS allows us to address the old questions. The real issue is the extent to which it allows us to ask new questions. Galileo, for example, when he acquired a telescope, had no idea what he was going to discover. He wasn't thinking, does Jupiter have moons? He found the moons of Jupiter, but it wasn't because he asked an old question. It allows us to create new priorities, and it is, I think, a powerful vision with a wealth of opportunity. So thanks for your attention.
We have plenty of time for questions to Mike. Again, please use a microphone. Raise your hands for our cyber participants.
Thank you. Thank you, Professor Goodchild. And when I saw your slide about if I have all of the computing power I want, and I really like those dots. And actually, before you give us an answer, my answer was I want them all instead of just one.
Oh, yes.
Do you think that's possible?
Oh, yes. Yeah, I wanted to argue that there were multiple options and we needed to be clear about the need to balance them. But yes, I think we can achieve all of them. I think the most problematic always in science is how to simplify and at the same time maintain rigor. That has always been a very major issue for us. How we deal with that, I think, has a lot to do with how we present ourselves, how the user interface presents us, the level of documentation that we provide underneath what we do. You present a simple interface, but then you have underneath that all of the complexity that anyone might ask for. And I think it does require us to address uncertainty in a much more comprehensive way than we ever have in the past. I think there are indications that uncertainty in the GIS domain has not been treated as it should. I cite examples where we bring up the whole world map and position the cursor, and at the bottom most GISs will give you the location of the cursor, and they will give it to what? 4, 5, 6 decimal places of degrees. And you do the math and you say, 5 decimal places of degrees, that's 1 meter. I've positioned a cursor which is at least 100 kilometers across on the Earth, and it's given me the location of the cursor to 1 meter. No, come on. This is ridiculous. Somehow we've abandoned, or the designers of that software have abandoned a very straightforward principle in science, which is that you never report the details of a measurement to greater than the accuracy of the measurement, right? And yet, I can get a GIS to tell me how far it is from Beijing, China, to Wellington, New Zealand, to 6 decimal places of meters. Right? That's a micron. We haven't dealt with uncertainty in the way that we should. And I think that is very much part of trying to simplify, but at the same time maintain a degree of adherence to scientific norms and a degree of rigor.
Mike, could you go back to that slide where you had the 4 items that you were suggesting? I think there are 4.
Well, you want this one?
Yeah, that one.
Yeah.
And you already loaded the conversation here. And do a little bit of a community consensus building kind of a thing here. And the community is in the room here. Yeah. For those who, everybody should look at these 4 items there. And Father of GIS, Dr. Michael Goodchild, has already loaded this conversation. So besides that comment that Mike used there, okay, because we could take that one off the list. Everyone have in mind one of these that's out there. What would you all suggest for the CyberGIS project? Because we have an opportunity to do this. Obviously, I'm being a little selfish here in terms of this question, but nonetheless, what would you all believe is the priority for these to be addressed by the CyberGIS project. If indeed, as Xiaowen has said, this project that's underway is the largest CyberGIS project underway right now. So it is this community that has the opportunity to move forward into a new era of computing, as the case would be. As Mike says, it's a game changer. What would be, from your all sense, the priorities here? So if we had a show of hands for those of you that would believe that the first one on the list is perhaps as important and more important than anything else on the list: simulation models, an ability to handle simulation models. I'll go back to Nina's comment yesterday afternoon saying that what she really wants, as if I'm interpreting her request correctly, is a infrastructure that allows to serve up space-time simulation models for her application. Is that something that is priority number one? So show of hands for simulation models, and don't be swayed here, because you'll get a chance to show of hands for number 2, 3, and 4 as well.
And then you could ask afterwards, which of those should we save for the next big project?
As the case would be. But there are always priorities, because you would expect to make a little headway on this project on something in order to justify that you're capable of doing the next project.
You might have multiple priorities too.
Yeah. Oh, yeah. No, there are. There are 4 priorities, right? These are priorities. They're all priorities, if I'm not correct interpreting what you said. So, but where does the energy go, right? What can the project do? So simulation models, show of hands. Garrett, go for it. It's almost done, right? So
I have to raise hands too. I supervise that.
What about number 2, synthesizing, analyzing large quantities of data? Okay. Reasonable. What's that, about 12, 15? Number 3. Okay. What about number 4? What about one that's not on the list? Anybody have one, want to venture to guess? One not on the list.
I think there needs to be overarching mechanisms to pull these pieces together.
Mm-hmm. Yeah.
How about number 5? Overarching mechanisms. Okay, good. Thanks.
Maybe one more question, one final question if you have. If not, let's all together honor Mike for